Welcome, webinar number 9, this time dealing with Seismic CPT. It's the 9th webinar in the series that Eijkelkamp North America is organizing on CPT, a monthly webinar that lasts about 30 minutes. I now introduce Troy Chips, the CEO of Eijkelkamp North America. Troy, the floor is yours.
Thanks, Gerald. I appreciate it. We're excited about today with the Seismic CPT. We've got Gerald Verbeek. He'll be answering a lot of the questions that Rob Lukacs from Advantage Distribution. He's the president and CEO up in Canada, and he's a partner of ours. We're excited about this opportunity that we have as Rob has put together a lot of these questions, and Gerald will be going over those. He's our technical advisor with Eijkelkamp North America. With that, guys, excited to see what you've got.
Hi, guys. It's Rob Lukacs here with Advantage in Calgary, Alberta. Quick introduction, and Gerald, if you want to do this first intro on this slide here, I can get going with a few questions after that.
Okay. Rob prepared a list of these questions that were shared with me in advance, and the reason that we disclose that is that you will not be surprised. I already have all kinds of slides with the answers in there. And the whole purpose of this webinar is really to have a discussion between Rob and myself, but also with you as the attendees. If you have any questions, please put it in the chat box, put it in the questions box, and then we'll try to bring in your questions, your follow-up questions as well, so that you hopefully learn more about Seismic CPT.
So yeah, our first question, guys, there's as I found going through a lot of these topics and Seismic CPT specifically with Gerald, you get into a lot of detail, and I'm hoping we can cover a lot of the broad spectrum of what Seismic CPT is today. And one of the first questions that I had for Gerald is the Eijkelkamp GeoPoint, specifically the SCPT technology. What is it exactly, and how does it work, and how is it different from something else in the market?
Okay, let's start with a picture that you've seen many times before, and that is CPT in itself, where we push a cone into the ground. By now you've heard, those of you that have attended this webinars series before, you've heard it many times, and we push a cone into the ground, continuous rate of about 0.8 inches per second, and we measure there the tip resistance, the pore water pressure, and the sleeve friction. And we push that cone with a speed of about 2 centimeters per second, 20 millimeters per second, or 0.8 inches per second, whatever unit you want to use, into the ground. Highly standardized, and we get all that information. But what you can do as well is that you put behind that cone that you see here on the right-hand side, we put an additional adapter where we have a seismic sensor. And what we now do is the truck or the pusher is still pushing the cone into the ground, still at the standard rate, but since you have to stop every meter anyhow to put a new rod in place, you stop there and you create a seismic wave. And that seismic wave, you do that at the surface by hitting a plate, whether it's under one of the hydraulic legs, as you see in the graph, or as you see in the picture on the left-hand side, underneath a tire of a vehicle that's in the area, about up to 20 feet away or something like that. That's no problem. You hit that plate horizontally, and that creates a seismic wave, and that seismic wave gets then recorded by the seismic sensor. And you do that test, say, every meter or every 2 meters, whatever depth interval you would like to have, and you record that information. If you are kind of very simplistic approach, it's just a plate with some ribs underneath it that you hit with a sledgehammer on the side, as you see on the left picture. If you want to go a little bit more sophisticated, you make it a pendulum, where you can now just pull the string, as you see in the second picture. You pull the string, lift the hammer, and let it drop. Sometimes it's a little bit easier, because if you have to do this, say 20 times both left and to the right side, or 20 different depth, hitting a 20 pound or 10 kg sledgehammer this many times may get somewhat tiring. So a pendulum is a little bit easier. And you can also use an automatic hammer that you see there on the right-hand side with an auto size system from Georgia Tech in this case, where you basically just have an automatic hammer that can create the seismic waves. What you heard me talk so far, though, is nothing about Eijkelkamp specifically. It's done in accordance with the ASTM standards for seismic cone penetration testing or downhole seismic testing. It's pretty much the same that is in the industry. There's really not that much of a difference there, because what you then do is you collect the data and you, based on the squiggly lines, as Paul Bain from Georgia Tech refers to them, and you figure out what the interval velocities are, and that's how you perform your seismic test. So are all the systems then exactly the same? Because as Rob asked in the beginning, what is specific about an Eijkelkamp system? The answer is no, it's not all exactly the same, and the main difference is the sensor. And that's why I want to pay a little bit more attention to what's on this sheet. You can use two types of sensors, geophones or accelerometers. A lot of the seismic testing is done with a geophone, but a geophone damps more, does not have necessarily the same type of response that you would like to get. So we strongly recommend the use of accelerometers, and all Eijkelkamp seismic systems now come with accelerometers. And the other thing is whether you use a uniaxial or a triaxial sensor. A uniaxial sensor is just a sensor that measures in one direction, either in the x-axis. Then you have a biaxial system that has two perpendicular axes, or a triaxial where you can also measure the vertical axes in the z direction. Even though for most seismic testing you only need to measure waves in the horizontal plane, so you could go with a uniaxial or a biaxial, but you don't necessarily need to go a triaxial sensor. Our recommendation still is to use a triaxial sensor. And the reason for that is that they're in the vertical component of the seismic wave, because when the seismic wave is created, you have all kinds of components, horizontal as well as vertical. If you measure everything, all components, you get a more complete picture of the seismic wave. And on top of that, you may also want to measure, instead of just the shear wave, you can also measure the compression wave, which very simplistically is generated when you hit the plate vertically. Or when you use a sparker to create a compression wave in the soil, then you need your vertical sensor. And it's easier if you already have it than that you have to replace it. Now, the sad thing is that when you are going from a very simplistic, simple geophone to the highest quality accelerometer, you talk about a cost difference of about $1,000. And that is why we don't understand why not all systems use high quality accelerometers, triaxial accelerometers, because when you see $1,000, it's a mere fraction of the overall cost of a seismic system. So to answer it in short, what your question was, Rob, our system really deviates from the basis that we have this high quality seismic accelerometer as a sensor, triaxial. And other than that, most of the systems function exactly the same thing, because you just have a human being hitting a plate and creating the seismic wave. Does that answer your question?
It does, yeah. No, it's a really good overview, Gerald, of how the system works and how it's different from maybe other products on the market right now. So here's my second question, and you mentioned the $1,000 to go to an accelerometer. Whether it's the contractor or the consultant who's going to be using this instrumentation and this tooling, is it an expensive upgrade or an expensive add to whatever services they already provide?
Right. It obviously is an upgrade. And when you look at, first of all, let's talk about the contractor. What he needs is the seismic adapter, the seismic data acquisition hardware, and then software, and a cable. Because when you do your regular CPT, that cable is not enough to bring all the data to the surface, so you need to replace a cable. All the other components that you have, your regular cone, your CPT data acquisition system, your pusher, all that stuff remains the same. So what you need in addition is roughly $20,000 worth. A little bit more if you want to talk about an automatic hammer, but if you just use a sledgehammer or create for yourself a pendulum hammer, as I showed you earlier, we're talking about $20,000 US, or since you're in Canada, about 26,000 Canadian dollars. That is to perform the test. And then if you want to analyze the test, because you also asked for the consultant, my recommendation is get a sophisticated software program that allows you to do filtering, that allows you to do the isolation of the seismic wave, and then you talk about roughly $6,500, or in Canadian dollars about 9,000 Canadian. Having said that, there are still a lot of people that analyze the seismic traces in Excel or do it manually. Now, if you can plot the traces, you could try to pick the first arrivals and do it by hand. We don't recommend that. There are all kinds of issues with that, and maybe at some point we'll talk about how that analysis is done. But this is roughly the cost that you're talking about for both the contractor to perform the test and for the consultant to analyze the test.
Okay. It's a really good basis. I know the data analysis may spark some additional questions for a later time. I don't know if we'll have time today, but no, that's a really good overview of the cost. My next question for you, Gerald, now that we've talked about what it is and what the cost may be or the upgrade, what exactly is SCPT measuring and how does it add value?
Okay. There are two ways you can do your seismic testing. Most of the time, what you're doing is you come up with your shear wave velocity, which is basically when you hit that plate that is sitting on the ground horizontally, it creates a shear wave in the soil that propagates down to where the sensor is. Other potential application is to get a compression wave. A compression wave is kind of the same type of wave that allows you to hear us now. Sound through air goes as a compression wave, not necessarily as a shear wave. And one of the ways that you can achieve that is by hitting the ground vertically, or with a membrane hit the ground vertically and get then a so-called P wave. But those two velocities, that is what you measure. So that is, we don't obviously straight away measure the velocity. We measure the arrival time of these waves, and then from the distance that the wave has traveled, we derive the velocity. So if I say that you measure the velocity, that's not strictly speaking correct. You measure arrival times and then derive velocities. Why do we do that? Well, with these velocity values, you know a lot more about the soil properties. And I give you here a couple of examples of that. The small strain shear modulus, G0, is a direct function of the shear wave velocity. Then you can also come up with the Young's modulus, not exactly just a function of the shear wave velocity, because it's also the Poisson ratio, because it's the Young's modulus is 2 times the shear modulus times 1 plus the Poisson ratio. But Poisson ratio is about 0.2 or something like that, 0.3. So it's roughly twice G0. But if you have both the shear wave velocity and the compression wave velocity, VP and VS, then you can also directly calculate your shear wave or your Poisson ratio that you see there. So those are kind of the parameters that you have and with these 3 parameters, you can derive a whole bunch of other things about the soil. So that is why doing this seismic CPT is so important, because now we can no longer just try to estimate the parameters based on the soil type, but we can actually measure them.
Great. And I think on the next slide, I saw the next question we have here, and I know as a true conehead, Gerald, you'll probably agree to this already, but do you see do you see SCPT as something that will be a mainstay in geotechnical analysis now, and do you see it going even more so in that direction in the future?
Well, sometimes I like these questions. It's I could just say, yep, absolutely, because like you said, I am a conehead, but I want to use this opportunity to really explain why you want to do this, and there are really 2 parts to it. One part is because you have to, but more importantly, because you want to. Let's first talk about the part that you have to. Here in the United States, back in the late 1970s, there was a program initiated that you see listed on the screen, and that program really tried to figure out what do we need to do to reduce the risk to life and property as a result of earthquakes. And that report that was generated was then, or the findings of that was incorporated in the IBC, the International Building Code here in the United States, to really see what do we need to do in our construction efforts to come up with a better standards of the construction, to have a safer type of structures when it comes to earthquakes. Now, the result of this whole thing was that the building code, and the same thing, by the way, applies to Canada and in many other places around the world. The building code started saying, listen, you need to come up with the mean shear wave velocity over the top 30 meters, so roughly the top 100 feet of the soil, which you see there on the right-hand side. And on that basis, if you measure that, and if it falls within the ratio that is given there, then you classify your sites to a certain seismic zone. And it is A2 to F. Obviously, in hard rock, we don't need to worry about it. And you just keep going down in the various parts. So the building codes, basically in all of North America, but also in many other parts around the world, require you to measure your shear wave velocity, and therefore you need seismic CPT. So that's the part where I say you have to do this whole thing because the building code requires it. Now, while it's great that you have to, I also think, and more importantly, is that you want to. And the reason for that is that it is a great tool to assess liquefaction potential. Let me explain to you. When you look at liquefaction, which means that the soil basically no longer has any bearing capacity, it's like quicksand, the influences or the parameters that influence liquefaction, and you see a whole bunch of listed here on the screen, the void ratio, the soil density, and I can go on and on and on. Those same parameters influence the shear wave velocity. So it's a good prediction. If the liquefaction aspect gets affected, then the shear wave velocity gets affected as well. Now, why is the liquefaction so important? When you looked at the major earthquake in Christchurch in New Zealand in 2010 and 2011, most damage was a result of liquefaction. And that liquefaction, especially near surface liquefaction, resulted in extensive foundation damage. So in order to figure out what is your damage potential of an earthquake, you need to think about liquefaction, and therefore you need to do something about the shear wave velocity, because then you at least know what the risks are. What does liquefaction look like? Something like this. You have a road then the earthquake basically liquefies the soil underneath it and it sinks down and you no longer have a road. Now, or when you have a building where part of the soil gets liquefied, no more bearing capacity, you get a situation like this. But my favorite picture when it comes to liquefaction is this one. You park your car, you go home, there's an earthquake, there's liquefaction, and when you come back, your car is kind of sunk into the soil, and it's hard to retrieve it there. You might as well say goodbye to your car. Now, because of that, because liquefaction causes all kinds of damage, and the way to find liquefaction is with seismic CPT or downhole seismic testing. This is why you want to perform seismic CPT to get a better handle on that liquefaction potential. On top of that, as I already mentioned earlier, with the seismic CPT, you can estimate the soil parameters, be it the shear modulus, be it the Young's modulus, or even the Poisson ratio, much more accurately as you have it in the field. So for those reasons, you really want to do seismic testing. Apart from the fact that you have to, in accordance with the building code, that's also a reason why you want to. So on that basis, yeah, the answer is absolutely, you should do seismic testing, and it will be as more and more areas get involved with earthquake potential. I think here in Texas and in Oklahoma and other parts of the country, because of fracking, that we have suddenly seismic activity that we never held for possible. It makes sense that you do your seismic testing.
And initially, when you went through this, when you started with the building code, sparked another question. Do you use seismic testing for more than just buildings and structures? And the answer is yes. Looking at some of the images of the roads or cars that have disappeared. So there are a lot of other applications than simply a building foundation that you'd use seismic testing for.
Right, and the other, but that's all falls in the category that you would like to use seismic testing. The building code requires it because let's face it, if you want to get a Poisson ratio, you can also take a sample, take it to the lab, and may a couple of weeks later finally get a value. Whereas with seismic downhole seismic testing, you pretty much have your results very quickly and more accurately because you measure actually in situ as it is in the field.
Okay. Thanks, Gerald. That's great. Now, now that we know where we can apply SCPT, is there anywhere where it is not recommended to conduct seismic CPT, or is it not possible in certain geographical locations?
Well, again, a relatively simple question. Are there locations where CPT is not possible? Absolutely. Are there places where it's not required? Yep. If you cannot push a cone, you cannot do seismic CPT. And we all know that if you cannot push a cone through rock, many people have tried, they continue to try, and they continue to break their cone. So it's really, it doesn't help you anything. You have to be able to push the cone. If you cannot push that cone, you cannot do seismic CPT. You can do other things, so you can get a borehole and then do a seismic test in the borehole, but seismic CPT, if the soil conditions don't allow it, you're going to have a problem. Where it's not required, a lot of places, what we see around the world is that you are doing in a given area X numbers of CPTs to get an idea of the soil profile, and a fraction of that, say a third or a fifth of the total number of CPT soundings that you do, are then utilized that with seismic CPT. But if you feel that there is no reason for the building code, or you don't need to know the soil parameters, you already have a good feeling for the soil parameters in that area, it is not necessarily required. You could argue that you don't have to do it because it takes time. As I said before, you push the cone into the ground continuously at that speed of 2 centimeters per second. But if you stop the process and you do your seismic CPT, that does take some more time, and time is money. So if you feel that you already know the properties of the soil in that area well enough, and there's no reason that the building codes requires you to do it, then you could say it's not required. But that gives you, you already hear from me that most of the time I would like to at least have on a job site some seismic CPT done, so that you simply have a better feel for the soil parameters.
Okay, great. So I know we're almost at the end here. If we can, maybe there's time for one more question, Gerald.
Okay.
So I've had this question asked to me, and can a CPT be completed on a water body, so on a barge or some sort of offland platform?
Well, in a way, I want to show briefly the previous slide. You say if you cannot push a cone, you cannot do seismic CPT, which then makes it very simple to answer this question. And the answer is, yeah, it can be completed on a barge or off land, because if you can push a cone, you can do seismic CPT. As long as we can push the cone, and we can push a cone off a barge, we can do offshore seismic CPT or offshore CPT. So as long as you can push a cone, you can do seismic CPT. All you do then is you lower the seismic hammer to the waterbed, and then you are in good shape. So it's not really whether you can do the seismic part, it's more whether you can do the CPT. And if the answer is yes, then seismic CPT is possible as well.
Okay.
Well, we have still we have room for one more question, and then we'll probably have to end this to stick within the time frame.
All right. So an important one for anybody who's new and getting into SCPT, how can one learn more about the field testing and also the analysis?
Well, let's focus on the field testing. Maybe the analysis will take next time, because I think you have some more questions about analysis as well. But how can you learn more? Webinars like this, and there are plenty of webinars that we have. We have a whole series, but there are also, Peter Robertson has some good webinars online as well. It will help you get at least an initial part about seismic CPT. We can also do presentations upon request, whether it's about this topic or anything else. For those of you that are listening, talk to your Eijkelkamp representative, sales representative, contact me. We can do those presentations upon request to cover the topic in general terms. And then finally, of course, we can provide training courses where we can come out to your site and really show you the nuts and bolts of seismic CPT and get you all the details. And we can do the training as long as you want, because I can talk about this topic for days and possibly even a week, and when we talk analysis as well, to really give you a feel for how to address those various parts. So with that, we have reached the bottom of the hour. So Rob, sorry, the other questions will have to stay till next time. Thank you again for being here, and stay safe, stay healthy, and look forward to seeing you in the future. Thank you very much.
Thanks, everyone.